This is joint work with my colleagues from the University of Maryland, the University of California, Santa Cruz, and Nayara Inc. Two authors of this paper, Shobeir, Fakhraei, and Madhusudana, performed much of the study while at IFWI, formerly known as Tagged Incorporated. In this work, we addressed the problem of detecting spam in social networks. This is a growing problem. A recent study performed by NextGate in 2013 found that the amount of spam had tripled in just half a year. As many as 1 in 200 social messages are spam, and 5% of all social apps are spammy in nature. So, what's different about social media and social networks which makes them such a target for spammers compared to the traditional web or to email? For a start, spammers have more ways to interact with users, including private messages, comments on photos, winks, and other interactive actions that can be directed at users. The social context of these interactions can be used to conceal a spammer's intentions. Spammers can also obfuscate the malicious nature of their content by splitting it across multiple messages, which poses challenges for traditional content-based spam filters, as well as for the human targets of spam. Social networks also typically make more information about users available to spammers, including information on their profiles and their friendship links, which can be leveraged by spammers for targeted attacks. Furthermore, spammers are getting smarter at social spam. Previously, a spam attack on a social network would look something like this. Here, the spam account named George messages a legitimate user of the social network. In this case, the user happens to be Shobeir, who is the first author of this paper, and George says to Shobeir, "Want some replica luxury watches? Click here, spammylink.com. Shobeir easily identifies and reports this message as spam due to the sketchy content of the message combined with a clearly fake photo of George Clooney and a lack of trust for this strange user called George. More recently, however, sophisticated social spam attacks aim to avoid detection by exploiting the social nature of the platforms. In the example on the right, a spam account, Mary, messages Shobeir, "Hey, Shobeir, nice profile photo. I live in the Bay Area too, want to chat?" Shobeir is unaware that Mary is a spammer, so he agrees, sure. The spam account engages Shobeir in a realistic-looking conversation and finally signs off by saying, "I'm logging off here. Too many people pinging me. I really like you. Let's chat more here at spammylink.com. This sophisticated social spammer is much more likely to avoid detection by algorithmic spam filters and by the user. The spammy content is hidden within a large amount of realistic social dialogue, which can confound content-based filters. It has also engaged the user's trust and engaged their interest and gained their trust, making the user much more likely to click on the link. Sophisticated spammers can also randomize the link and even spread the link across multiple messages to avoid detection by content-based spam filters. So in this paper, we aim to find such social spammers in social media websites. We were particularly motivated by the site tagged.com, although our approach can be applied more broadly to any multi-relational network, which includes all modern digital social networks. Our motivating site, Tagged, is a social networking site which connects people through social interactions and games. Tagged is kind of the opposite of Facebook. You go on Facebook to chat with friends you already have, or you go on Tagged to make new friends that you don't already have. Tagged was founded in 2004 and has over 300 million registered users. We analyzed a subset of the data containing 5.6 million users, of which around 4% were labeled as spammers. The subset includes 912 million interaction links between users. Spam detection in social networks such as tag.com can be formalized as a classification problem in a multi-relational, time-evolving network. The nodes of the network can be categorized as either legitimate users or spammers, and the goal is to classify the nodes into these two categories. The graph consists of links between users, which correspond to actions that the users take, and which are associated with a timestamp. In Tagged, the possible actions include viewing profiles, messaging, pokes, winks, reporting abuse, and so on. To make the problem formulation concrete, let's look at the example network shown in this graph. At time t equals 1, a spammer views the profile of a legitimate user. At time t equals 2, the user messages another legitimate user. Then at time t equals 3, another user unknowingly pokes an account, which happens to be a spammer. At time t equals 4, a different user reports the spammer to the site administrators along the identification of the spam account. It should be noted that while user reporting of spammers provides a strong signal for spam detection, it has limitations in terms of the coverage of the spammers and is also noisy, so it is insufficient by itself to rapidly and accurately identify all the spammers in the network. Okay, having described the setting, I can now introduce our novel approach to detecting spammers in social networks, and specifically the tag.com network. Spammers are using the social nature of social networks to disguise their activities, and our approach fights fire with fire by using the social network itself to find the spammers. We propose to classify spammers based on 3 types of signal: the graph structure of the multi-relational network, the sequences of actions performed by the users, and the abuse reporting behavior of the accounts. Note that we do not consider content information here for several reasons. Firstly, in social networks, content-free methods are preferable for privacy reasons to the extent that this is possible. Content-based filters are also more easily manipulated by spammers. Here, we're mainly interested in detecting the sophisticated spammers that have already passed traditional spam detection methods, including content-based filters. In any case, our method can also be combined with content-based filters if this is desired in a deployed system. Let's start with the first part of our approach, using the graph structure information to detect spammers. We begin by extracting graphs for each relation, where each relation corresponds to a type of action in the network. For instance, we extract the message graph between users, the friend request graph, the wink graph, and so on. We then extract a number of features from the graphs for each relation, thereby representing each user in the social network with a feature vector. For each relation graph, we extract the following 8 types of features for each node in the network: the page rank of the node and its degree statistics, including the total degree and its in-degree and out-degree. Intuitively, these features measure the extent to which the node is connected to the rest of the network. We also compute the k-core of the nodes, which is a centrality measure that is computed by recursively pruning the least connected vertices. The k-core value of each node is the iteration in which it is pruned. More central nodes will get pruned later, so they'll have higher k-core values. We also perform graph coloring and encode the color identifier of each node as a feature. We compute the weakly connected components of the graphs and extract component identifiers and the size of the components as features. Finally, we count the number of triangles in the graph that each vertex participates in. The triangle count is a measure of the connectivity of the graph around the node. And triangles are also considered important structures in social network theory, such as triadic closure and balance theory. So these 8 kinds of features are extracted for each of the 10 relations in the multi-relational network, which are viewing user profiles, friend requests, sending messages, sending love, sending winks, the buying and wishing actions in the interactive pets game untagged, yes or no responses in the tagged meet me game, and reporting abuse in the network. After feature extraction from the multi-relational network, we have encoded each user with a feature vector capturing key properties of the graph structure relating to that user. We can then apply standard supervised classification techniques. In this work, we use gradient-boosted decision trees, which are a relatively powerful and flexible ensemble approach for a nonlinear classifier, though we could also plug in any other classification algorithm here. So here are some experimental results for spammer classification using the graph structure features alone. First, if we use all 8 features, but for only one relation in the multi-relational network, the result for the best performing relation is an area under the precision recall curve of 0.187 and an AURC of 0.803. If we instead use all the 10 relations but only one feature type, the best performing feature gives better results. The best performing feature was the page rank of the users, which gave an AUPR of 0.285 and an AURC of 0.809 when used with all 10 relation types. So it is better to use multiple relations than to use multiple features if we could only choose one of those 2 options. Of course, we can use both multiple relations and multiple features, and we find that the performance improves again when we use all 10 relations and all 8 feature types, with an AUPR of 0.328 and an AURC of 0.817. So using both multiple relations and multiple features leads to better performance. So far, our approach has considered the graph structure of the multi-relational social network, but we haven't yet leveraged the temporal information in the network. We make use of the dynamic nature of the social network by analyzing the sequences of actions performed by the users. Our hypothesis was that most spammers are computer programs, and their predefined behavior in terms of the sequences of actions performed may give away their automated nature. It's important to note that sequence mining is only possible because social networks are multi-relational, i.e. there are multiple types of interactions between the users, and they are dynamic, with the interactions occurring over time. This is in contrast to the traditional notion that social networks can be understood by analyzing just one adjacency matrix. A simple approach to extracting feature vectors from sequential information is to compute counts of k-gram features, such as bigrams. In this example, user 1 performed the actions message, profile view, message, friend request. We count the number of occurrences of pairs of consecutive actions, e.g. message followed by profile view, using a sliding window of length 2. We also used a slightly more sophisticated probabilistic model-based approach for classifying sequence data. Our model posits that the data are generated via a mixture of Markov models, as shown in the graphical model diagram and joint distribution on the slide. In the model, each class, spammer and non-spammer, is associated with a Markov chain, which generates the sequence of actions for the user. This type of model is sometimes called a chain-augmented or tree-augmented naive Bayes model. We train the model via map estimation and compute the log posterior probability of the classes, as well as the odds and log odds of the classes, and include these values as features for the classifier. After combining the bigram features and the predictions from the probabilistic model into a feature vector for each user, we construct a classifier in the feature vectors to predict spammers. This slide shows the results for using the sequence-based features in isolation. We find that the mixture of Markov models provides little benefit, after all, to the classifier over simple bigram features. However, it does not add much computational overhead if we're already computing bigrams, so we still include the features from the probabilistic model in our final approach. The classifiers with bigrams and the predictions from the mixture of Markov model has an AUPR of 0.468 and an AURC of 0.86. Okay, here are the full experimental results for each of the classifiers using the different feature types. All of our results were obtained using tenfold cross-validation. We obtained ground truth spammer labels from a set of accounts that were flagged and deactivated by tag.com's administration team in the time since our data sample was collected. So on the left, we have the precision recall curve, and on the right, we have the RC curve. We find that the sequence features, shown in green, perform better than the graph structure features, which are shown in red. However, a classifier with both graph features and sequence features together performs better than either feature type by itself, as we can see from the light blue curve. Finally, for the complete model, we additionally include 3 demographic features: age, gender, and time since registration. Age and gender improve the classification results as they're indicative of behavioral patterns, e.g. the way that teenage girls behave is different to the way that 50-year-old men behave, or at least one would hope so. The nonlinear classifier can leverage these patterns during classification. The age of the account is also a useful signal because legitimate users are typically in the system for a longer time. The full classifier, with all features, performs the best, is shown in the dark blue curve. Using this classifier with all of the features, we could detect about 70% of the spammers that had passed traditional filters and needed manual labeling with around 90% precision. To deploy this model in practice on the tag.com platform, the model can be repeatedly retrained on relatively short intervals in order to adapt to adversarial reactions by spammers. And the features can be computed in parallel, and many of them can be kept up to date incrementally also as events occur in the network. Even computing the features from scratch is not that computationally difficult, especially at an industrial scale, as we are able to compute the features in minutes using Graphlab Create on a single MacBook Pro laptop. So far, we've used the graph structure and the action sequence information to detect spammers in social networks. In the third and final part of our approach, we make specific use of the abuse reporting systems available in social media platforms such as tag.com to detect spammers. Like many social networks, tag.com provides an interface for users to report other users for their abuses to the system, such as spamming. This reporting system is valuable as it very directly identifies spammers for us. However, the reporting systems are very noisy for several reasons. People have different standards for labeling users as spammers, which can lead to errors, but more dangerously, there are adversarial reasons for errors in the reporting system. Spammers report legitimate users as spammers in order to increase the noise in the system, and even human users abuse the reporting system by reporting their opponents in social games. Our goal, then, is to clean up the results of the reporting system. So we accomplish this by making use of the reporter's previous history, as well as collective reasoning over the graph of report actions in the social network. More specifically, we use a graphical modeling approach to clean up the reporting system. Using a logic-based modeling language, we define a graphical model for jointly inferring the spam labels together with the credibility of the users at reporting the spammers. The graphical model allows us to propagate label information across the network. We construct a specific kind of graphical model called a hinge-loss Markov random field, which is a type of undirected graphical model over continuous random variables, and where the feature functions are hinge functions. These models are highly scalable and can be specified using a declarative modeling language called Probabilistic Soft Logic, PSL. A program in the PSL language specifies a graphical model via weighted logical rules. The rules are instantiated as potential functions in the resulting hinge-loss MRF graphical model, and they penalize the probability of a state that does not satisfy the rule, as measured by its distance to satisfaction. PSL and hinge-loss MRFs were developed in Lise Getoor's group at the University of Maryland and now at the University of California, Santa Cruz. So to begin with a baseline Psl model, which uses the reports but performs no further reasoning. This model consists of two simple rules. The first rule simply states that users that are reported as spammers are in fact more likely to be spammers. The second rule encodes the prior knowledge that most users are not spammers. We then extend this model to make use of the credibility of the reporter. Here, the credibility of each user is a latent variable which is also inferred along with the class labels. The first rule states that if user v1 is credible and they reported user v2, then v2 is more likely to be a spammer. The next two rules encourage the latent credibility variables for each user to be similar to a prior guess at the user's credibility, which we obtain from their accuracy on the training data. The final model, building on this model, is an MRF for jointly inferring the spammer status of the users together with their credibility for reporting spammers. The first three rules encode the collective reasoning of the model. If user v1 is credible and they reported v2 as a spammer, then v2 is likely to be a spammer. If v2 is a spammer and v1 reported them, then v1 got it right, and so they're likely to be credible, and so we should believe them next time. If, on the other hand, v2 is not a spammer, then v1 got it wrong, so they're not likely to be credible, and so we shouldn't believe their other predictions either. Okay, now that we have defined our models, here are the results for our cross-validation experiments for spammer classification using abuse reports. We find that the model which simply uses the reports is beaten by the model which also makes use of the credibility of the users, which in turn is beaten by the model that performs collective reasoning to infer credibility together with the spam labels. The final model achieves an AUPR of 0.884 and an AURC of 0.873. To conclude, our approach for detecting spammers in social networks such as tag.com has three components. We first build a classifier by extracting features from the graph structure of each of the relations in the multi-relational network. We then extract features from the sequence information of the user's actions. Using both feature types together improve performance, especially when combined with simple demographic features. The full classifier had an AUPR of 0.779, and it could identify 70% of the spammers that passed tag.com's deployed spam filtering at a precision of 90%. In a complementary approach, we also showed how to refine the outputs of the abuse reporting system using a graphical model to perform collective classification and jointly infer the latent spam reporting credibility of each user together with the spam labels of the user. This improved the AUPR of spam reporting from 0.674 to 0.884. We will release our code and a subset of the data at the URL at the bottom of the slide. Before concluding the talk, I would like to thank my collaborators, Shobeir Fakhraei from the University of Maryland, who performed the majority of this work, partly doing an internship at tag.com, as well as Lise Getoor from UCSC and Madhusudana from IFWE, formerly known as Tagged, and who is currently at Nyara. Shobeir would also like to thank many colleagues from IFWE and Data, formerly known as Graphlab. Thank you very much for your attention.
Thank you. Any questions for 2 minutes?
Very nice work. Nice work and very nice presentation. I was wondering about the interarrival times of the activity. Did you study that? I noticed you did the Markov chain, but interarrival times, if they have a very small variance, then it's probably a robot.
Yeah, we didn't actually look at that, and I totally agree that I think that would be a very valuable signal. Right now we only use the sequence information, but yeah, totally, I think it's worth looking at whether the arrival times are realistic. Thanks.
So one question for me is actually, which feature do you think is the most powerful in this problem?
So we found that the sequence information was really useful, and it performed better than the graph structure features. The last piece was using this reporting graph and cleaning it up, and so that gets a higher accuracy than the first method using all the features to try to predict spammers. But then, even though it's more accurate, it can only find the users that were reported. So there's kind of a trade-off here, right? Like we could use those reports to get just the top few, or we could use like the features and especially the sequence features to get all the others that were not reported. So they're kind of complementary. Thanks.